Okay, hello everybody to this week's ISGC seminar talk. This week's speaker is Jan Harms. He got his doctorate, the German equivalent of a PhD from the Leibniz University Hannover, where he worked at the Albert Einstein Institute. And currently he is a professor at the Gran Sasso Science Institute in Italy. Thank you very much, Jan, for giving this talk. The stage is yours.
Thank you so much for also this kind invitation that I can present about my work here. Okay, it's about the Lunar Gravitational-wave Antenna, which is a new concept, relatively new, now a few years old, to measure gravitational waves. And I would try to tell you why we want it and what we can do with it. Let's start with the scientific part of the story. So essentially, when you look at the planned and existing detectors, then this is mostly focused around this span from fractions of a millihertz, where up to a few tens of millihertz, where you can in the future measure gravitation waves with space detectors, like for example the LISA mission. Here the terrestrial detectors, of course, the LIGO and Virgo detectors that are already existing, the Kaga detector in Japan, but also including the future detectors that we have proposed and that we are working on, like the Einstein Telescope that is to be located in Europe, and hopefully also the Cosmic Explorer in the USA. Now, these two observation bands, and I'm leaving out very low frequency concepts like the pulsar timing arrays and cosmic microwave background polarization measurements. So in reality, the total span of frequencies that we observe or try to observe at the moment is much larger. But these are here, let's say, this is the range of frequencies that we can access with our high precision detectors for direct observations of the effect of gravitational waves on our instruments. And so now on Earth, you cannot go to arbitrary low frequencies with the observation. That has to do with the environmental noise, especially the atmosphere, the oceans. They're producing a lot of gravitational fluctuations that mask any gravitational wave signal below a few hertz. Now, you could try with some sophisticated ideas and concepts to reduce that noise a little bit, but it will not enable gravitation wave detections at such low frequencies. At least it would be a not very strong concept. Instead, the LISA detector will, as I already mentioned, these type of detectors measure up to few tens of millihertz. Now, that leaves a gap. And this is something that we call decihertz detectors. And there is a lot of science in this band, which is currently not covered by any already approved or built or existing detector. There are mergers of Newton star of white dwarf binaries, primordial backgrounds to be discovered, tile disruptions, intermediate mass black holes. I will go into these sources in the coming slides. The point is just, there is a scientific motivation to have something observing between the space detectors and terrestrial detectors in terms of frequencies. So let's look at the science that we could do. There are early works on decihertz gravitational wave science in the 2003. Sturl Finney at Caltech and others were asked by NASA to answer a specific question. They knew at that time that there were models about a stochastic primordial gravitational wave background, similar in nature, if you want, at least phenomenologically to the microwave background. And the question was, what do you need to build to see such a primordial background? And this was a mission study, a conceptual study, of the feasibility of such a thing. Not technology-wise, they produced some concept how this detector could look like, but it was really more a mission idea, and then some motivation how that one could measure these stochastic backgrounds. And then based on that study, there were follow-up works by Cutler and myself, Kurt Cutler, myself, and Kurt Cutler and Daniel Holtz. Now, these studies talked about the primordial background, essentially the detection of all compact binaries composed of neutron stars and black holes that are emitting in the decihertz band. Dark matter distributions could be studied via weak lensing measurements, so weak lensing effects on gravitational wave signals, essentially changing their amplitudes, this could be observed and analyzed. A large number of extragalactic double white dwarfs, Hubble constant measurements, pre-merger warning of neutron star binaries, first observed in this decihertz band, and then month later merging essentially in the band of terrestrial detectors. So these were the initial scenarios under investigation and really showed that there's an enormous science case for decihertz gravitational wave detection, but they really left open still the question, how would you build the detector? Is it technologically really feasible? But let's stay for a while on the science case. So here you can see a plot, for example, with respect to the observation of a primordial gravitational wave background, where you have here omega GW, which is the fraction of energy density in gravitational waves. And so here you can see what we call primordial inflation or slow roll inflationary model, which predicts, given the upper limits that we have today from the polarization measurements, but also based on some of the models, you see essentially that here a very, very tiny fraction of the energy density would be connected to gravitational waves. And now the question is, here you see essentially in these units here, you see the sensitivity that you can reach with Einstein Telescope and Cosmic Explorer. Here, some of the fancier space detectors, Big Bang Observer, the Japanese DeSigo concept, IH is an atom interferometric concept. And here you see LISA. So first of all, why do we dive so deep into the sensitivity in this frequency band at 0.1 hertz? Why don't we try the same with the terrestrial detectors? Or why doesn't LISA go so deep? And there's a specific reason to it. And that is exactly the motivation, the initial motivation for proposing the decihertz detectors. So it is connected to the background of double white dwarfs. Double white dwarfs, there are possibly millions of them in our own galaxy. And if you take them all together, and including the the extragalactic double white dwarfs, so all of them, the full cosmological distribution, they will create a background, an astrophysical background, which in omega is described by this spectrum here. And so how, you can see that there is a peak in energy density, at maybe 10 millihertz. Now, just to keep in mind, these models are from, 2004 or so. So they have been updated since then, but it's more or less still valid. So you see a peak of the energy density, and then it's falling rapidly, the energy density. Why that? Because it turns out that the white dwarf binaries merge at these frequencies, depending on their masses. And above the merger frequency, of course, there's not much energy anymore emitted. And so that explains the sharp fall of energy density produced by the collection of all double white dwarfs in the cosmos, if you want. So LISA is measuring exactly here around the peak towards lower frequencies. Now, it turns out that there's no way, you can resolve some of these double white dwarfs with LISA coming, existing in our own galaxy, but you cannot possibly hope to resolve all of these individual signals. And that's nothing to do with how well you make your technology or your data analysis methods. There is a fundamental limit to how well you can resolve individual signals here, because the idea could be that you observe, you resolve all of them. That would be nice if you could do it, resolve them all individually, and then subtract those signals one by one from the data, and then hoping that you can reach, reduce the background here by orders of magnitude to then finally be able to see something very weak caused by, by primordial phenomena. And so that would be the idea, but it turns out it's fundamentally impossible because there's simply not enough information in your data to resolve all of these binaries. So that is the explanation why LISA, even if you make the detector, a million times better, will not be able to be more sensitive towards a primordial background because of this huge foreground produced by white dwarfs. So that means you have to go to higher frequencies, and that's where the whole initial idea for the decihertz detector concept came from. That was the outcome of the Stirl-Finney study. Okay. Now, I will already mention, this is now a collection of sensitivities. Now here, the future, hopefully future gravitational wave detectors on Earth, Einstein Telescope, and Cosmic Explorer. Here, the LISA detector, adopted by ESA and moving forward for launch in 2035. And here in the middle, we would like to have another detector. And now you saw here that these detectors, like Big Bang Observer, DeSigo, and so on, these are like really sensitive detectors. The issue here is that the technologies for these detectors don't exist yet. And in some cases, I would claim that we don't even have an idea for how to develop these technologies. So that is, a very, very optimistic and ambitious target to get to the performance of these detectors. That's the main discussion that we're having in the field right now. Like, but if you cannot build these at the moment, then what can you actually build? That's a tough question. Now, I will explain more about this. We proposed the Lunar Gravitational-wave Antenna, and then you could achieve a sensitivity like this one here and fill the gap between LISA and the terrestrial detectors. Fine. Now, we have looked then with respect to LGWA for such a relatively modest, it's actually still extremely challenging, but for this relatively modest sensitivity goal compared to Big Bang Observer and DeSigo and so on, we have looked at the science case and produced this paper that you can also find online, open access. And in this paper, we're looking at multi-messenger observations, so where essentially a source emits electromagnetic signals together with gravitational waves. Then what is the gravitational wave science that you can do without any electromagnetic observations? And then I will explain this better later on. There's also a chunk on lunar science because of how we want to realize this detector. Okay. So with such a modest sensitivity goal, again represented by LGWA, what could you now do? For example, here it's very hard to see, but here is essentially the edge of a contour here, or a contour, which we call the detection horizon. And that is of the Einstein Telescope. So the Einstein Telescope will be able to see gravitational wave sources out to redshift of 100. And this peak is at a mass of the compact binary of around 10 to 20 solar masses. Okay, so that is important. Now you would say like, okay, this is already overkill. Like, why do you even want like a redshift 100? I mean, there we are deep in the dark ages, and what do we expect? Well, first of all, some people do have expectations at these high redshifts. For example, the merger of primordial black holes, which is at the moment considered a more speculative way for black holes to form. But there are well-motivated mechanisms for black holes to form before the first stars. And now those could be revealed even at highest redshift. But now don't think only about these detection horizons like being interesting. This redshift 100. This is also an indication of how strong the signals are. For example, that you see at redshift 10. So if you have a horizon of 100 at these masses, then at redshift 10, you still have a quite decent signal to noise ratio, not decent, a high signal to noise ratio, which really enables you a quite complete study of the, for example, black hole populations at those redshifts. So these horizon plots are very important because they give you a clear indication of the science capabilities of such detectors. Now, here is the LISA detector, and also here it ranges now into the hundreds of redshift for a few thousand or several thousand solar masses. So the best observation is done at much higher mass, and so there is this connection between mass and frequency really. LISA is a low frequency observatory, which is optimized for higher mass observations. And here in the middle, now we have the peak for like 1,000 solar mass binaries of LGWA out to tens of redshift. Okay. So that is very interesting because then with these three together, you would get a quite complete picture of black hole populations, even out to high redshift, of astrophysical origin as well as of primordial origin. And then you could study things like the formation of the very massive, supermassive black holes at the center of galaxies, why JWST, for example, sees them so early in the universe. How did they form so quickly? Now, these are really tough questions to answer at the moment, and these observatories will make a huge impact on those models. Okay. The other thing is that there are binaries that are much lighter, for example, Noon star binaries, and they do not merge in the band of decihertz detectors. They merge, as you probably know, in the band of terrestrial gravitation-wave detectors. But if you observe the Newton star binary, for example, in the decihertz band, then you could do two things. First of all, you would detect it, and you would be able to predict, not very accurately, but sufficiently well, the merger time of this Newton star binary. And so you would tell the terrestrial detectors and maybe the electromagnetic observatories, hold on, within like 2 weeks and 10 days, 2 weeks and 3 days or something like that, there will be a BNS merger. So be prepared. In addition, however, it's getting better since the frequency evolution of these Newton star binaries is very slow. That means like you are in this band here. So you're observing them for a month. And during these months, you collect so much information about those signals that you can even localize the sources very, very accurately, like sub-square degree precise localization. So not only will you be able to tell more or less when this Newton star binary is going to merge, you will also going to point to the sky and say like, that's where it's going to merge. That's where the source is. And so please point your telescopes in that direction. That's of course not relevant for the gravitational wave detectors on Earth, but it is relevant for all the electromagnetic observatories that might want to catch the weak electromagnetic signals that are produced by these sources from the very first moment. And so that is a very exciting capability. With respect to white dwarf mergers, which are only observable in the decihertz band, because that's where they actually merge. If you, for example, compare the horizon of LISA to white dwarf binaries, LISA will essentially only see galactic white dwarf binaries or in the Magellanic Clouds. So very, very local structures, if you want, that you can explore here. With a decihertz detector, even with a relatively modest sensitivity like LGWA, you will be able to see out to tens of megaparsec, which at this point already includes a good number, a high number of galaxies, and really boosting the number of signals that you can catch in this way. And so why is that so interesting? Because we, for example, don't understand yet what is the progenitor of a supernova type 1a, which are very important electromagnetic signals that are also being used for the cosmological distance ladder. And one of the possibilities is that the progenitor of these supernovae are two white dwarfs merging. There's also this single degenerate scenario where one white dwarf is accreting matter from an orbiting star. Now, these two are there, and maybe both of them contribute to the full number of supernova type 1a, but nobody really knows. I mean, there are all kinds of models and inconsistencies, and in addition to verifying which of these channels is the correct one, or if both of them contribute, you could even, through the information that you get from the gravitational wave signal, maybe improve the calibration of your cosmological distance ladder later on. So these are all possibilities that open. Okay, I just glanced over this. There have now been recent, more detailed studies about the population of white dwarf binaries merging within a few tens of megaparsec, considering also the different types of white dwarfs that exist depending on their masses and so on and so forth. And so let me switch to another interesting aspect. For example, core collapse supernovae. Now, historically, they were discussed as a high frequency signal because when you look at the numerical simulations, essentially, they tell you, here you see a series of spectra produced from numerical simulations of Kokolab supernovae, and the emission of gravitational waves peaks maybe at hundreds of hertz. Now, how is that interesting to Decius detectors? Well, it turns out that if you run these simulations carefully with all effects included, and by the way, this is a very recent achievement. For a long time, these numerical simulations didn't even manage to make an explosion of a supernova, of a Kokolab supernova. So now these models are finally producing exploding Kokolab supernovae. And here it turns out that there is the emission of signals, which is really called the memory effect. That's a more exotic effect, a nonlinear effect happening. Well, there's actually what we call a linear, nonlinear memory effect. But in any case, in any case, there's a phenomenon happening with the asymmetry in the emission of, for example, neutrinos and matter, and they lead to a step-like disturbance in space-time that propagates out. And this is a quite strong signal, and it's low frequency because it's a step function, okay? So, and these contributions are very strong, much stronger than the hundreds of hertz signal. And so now the possibility is that you can see that signal, or maybe with future terrestrial detectors that are sensitive at low frequencies, like Einstein Telescope, or with decihertz detectors. So I think that's a very exciting possibility. Okay. Then another phenomenon, very interesting, now again connected with the electromagnetic world, are the tidal disruptions. For example, a white dwarf and a neutron star binary, when they get close to each other, when those two objects get close to each other, then the white dwarf at some point get disrupted tidally by the neutron star, and then the matter spills out and forms an accretion. So the whole process here is shown here. And so here you can hope that these signals you can observe with a decihertz detector. Again, decihertz because there's a white dwarf involved. And so the size of that object is such that the merger also here happens in the decihertz band. And then, of course, here you can hope to also have an electromagnetic counterpart to observe, which gives rise to interesting multi-messenger studies. Okay, now back to this schematic here. The question remains, what is the detector that you want to build here? Fine. Now there have been different answers, actually a long list of ideas what you can do. Levitated superconducting spheres, spin nanodiamonds, torsion bars, juggled and jiggled interferometers, ring accelerator detectors, so particle ring accelerator detectors, planetary scale binary resonance detector, atom interferometers, frequency com detectors, liquid helium, a laser interferometer on the moon, atomic clock arrays. Now, this is a series of papers and probably not complete. In fact, I know that there are a few other concepts, maybe slightly less convincing, but just to say, there is this embarrassment of proposing a clear technological path forward to realize the first decihertz detector. So this embarrassment essentially led us in the end to look, I studied several of these ideas very carefully, and in the end ended up with the lunar gravitational-wave antenna as what I think is the most convincing concept. Now, how does it work? Okay, so here some of you might have seen this video already. It was produced with the first detection of a black hole binary by the LIGO detectors. So here a gravitational wave peak is propagating out from that source after the merger. And so, as you know, it is propagating through the universe without being really affected much by matter, except maybe for some lensing. But now, when it comes to Earth, for example, then this gravitational wave will induce oscillations of the Earth, because you can imagine that the space-time fluctuations that are passing are like a hammer on a bell. And so you have to understand what are the notes that the bell here is playing. What are the eigenmodes, the normal modes of Earth? And that's essentially telling you how Earth responds to a gravitational wave signal. And it allows you with such a response model to predict, what you can actually observe in terms of gravitational waves. It turns out that this was tried in the 60s, and already then they came pretty much to the conclusion, that you cannot detect in this way gravitational waves on Earth because there's too much background noise. Now, myself and a student, at some point postdoc, at some point faculty, the two of us were studying this problem very carefully, applying the sophisticated data analysis pipelines developed essentially by LIGO and Virgo. And we applied them to sensors that observe the vibrations of the Earth. You could, call them seismometers because that's what most of them were when we did the studies. And after doing the best we can, using decades of data from seismometers around the world, correlating their data and doing all kinds of tricks, we achieved a very interesting result in the sense that we were beating any other gravitational wave measurement in the decihertz band by many orders of magnitude, by more than 10 orders of magnitude in sensitivity. But we came to limits and we didn't detect gravitational waves. We set upper limits. And it was clear to us that, okay, this thing works really well, but on Earth, there's too much background noise. So we should not expect this to ever work on Earth. And that's where then the opportunity came 2020 when ESA was calling for ideas. What is the scientific experiment that could be brought to the moon with the Argonaut lander? So at that time, it was called the Large Logistics European Lander. Now it is renamed to Argonaut. And so we proposed in 2020 the Lunar Gravitational-wave Antenna. Now, also, that idea, to be honest, is not new. Already during Apollo, a seismometer, or what they call the lunar surface gravimeter, was deployed on the moon to measure gravitational waves, and that didn't work. So there was a failure with the experiment, but also that instrument would not have seen any gravitational waves, even if it had worked perfectly. So we are quite aware of the limitations, and we know today what is the sensitivity that you have to reach with these sensors and what are the challenges. We know practical issues like you need a good thermal stability for a gravitational wave detector. You need very low background noise. And so that is the reason why we proposed LGWA in this way, deploying 4 seismic stations inside a cold area on the moon, which is essentially a permanently shadowed region at the south or north pole of the moon, which permanently shadowed means like that never ever do you have a direct sunlight hitting the surface there, which means that these can be very, very cold, continuously below 40 Kelvin, for example. And so the array here, instead of a single sensor like here in Apollo, we propose 4 so that we are able to distinguish between gravitational wave signals and seismic background events. Okay. Now, the key mission features is like you need to create very, very sensitive accelerometers. So with femtometer precision at the hertz, picometer, sub-picometer throughout the decihertz band in any case, you exploit the extremely low seismic background on the moon. I will show a little bit more about this. You will exploit the extremely low temperature and high temperature stability inside permanently shadowed regions at the lunar poles. And you have the station array to mitigate the noise from the seismic background. Now, the Apollo seismometers only established a upper limit for the seismic background because they were not sensitive enough to really observe it. They observed the moonquakes for sure. There were many moonquakes that they were able to observe with these 4 long-lived stations. But the real always present seismic background, so the thing that would really limit your sensitivity, that is unknown by observation today. So the only thing that we can do at the moment is modeling the lunar background. And it is predicted that meteoroid impacts likely produce the dominant, always present seismic background at a few tenths of femtometer per square root of hertz in this decihertz band. Okay, fine. Now, there's a deep connection between the lunar gravitational-wave antenna and the internal, lunar science, because we care a lot about the deep internal structure of the moon, and we also care about regional structure around the deployment site in terms of craters and geology. And so all of these things are now being put into numerical models of the moon, kind of digital twins that we use to then run seismic simulations to predict what is the seismic background more accurately, but also how does the moon respond to gravitational waves. And so we have some models that are already partially numerical, but they are not yet taking enough detail into account to be considered reliable at this point. And so in fact, in my point of view, how the moon responds to gravitational waves is one of the biggest question marks that we have at the moment when it comes to LGWA. Now, you also have to be able to calibrate a gravitational wave detector very accurately. So, for example, we can reach percent to few percent calibration errors for LIGO and Virgo detectors today. For the Einstein Telescope, we would like to have like 0.1% calibration errors or less. That's very ambitious, but that's what we need to fully exploit the content of our data. Now, what we intend to do as one of the ways to help that process for the lunar gravitational wave antenna, which, you have to calibrate the response of the moon to gravitational waves. How do you do that? Well, as I said, some of these signals are being observed by both LGWA and Earth detectors, like, Einstein Telescope and so on. So we can take the very good calibration from the Einstein Telescope and trace the amplitude of that signal back to when it was in the band of LGWA, and then compare the observation that we have in our sensors with the accurate model of the gravitational wave. And the relation between those two is really the calibrated response of the moon to gravitational waves. And this is probably the most precise way how we can calibrate the moon. And by the way, it also allows us to do a tomography of the moon, of its internal structure, using gravitational waves as the probing waves in this scheme. Something that we are currently preparing for publication, this idea. Okay. Now, the seismic background very quickly. Not so clear. There are some models like how meteoroid impacts are distributed across the lunar surface, which is very important for us. Now, in this observation from the Earth of impact flashes, here there's a lot of heterogeneity or non-uniformity, which is probably mostly observation selection effects. So this part here, that there's a gap of impacts here in this central region, is an observation selection effect. You have less time to observe with good sensitivity in this part here. This similarly for the moon, for the poles. But even though here the predictions are also by models that there are less impacts at the poles compared to the equator. Now, this is something to be confirmed because not everybody agrees about this. But that would be very, very interesting and important also to understand for LGWA, since it is located at the poles. If there are truly less impacts in the end, then it would mean that we might have a strongly reduced seismic background at the poles compared to the equator. Now, that's just a wish at the moment, with some indication from models, but to be confirmed. We also have to study magnetic fluctuations at the lunar surface very briefly. That has to do with magnetic susceptibility that we have in our instrument. So we have to make sure that the environmental magnetic fields that are fluctuating due to different effects, that they are not producing excess noise in our measurement. So this is interesting more for people who plan future lunar missions, that magnetic data from the lunar surface is highly interesting to us. So we definitely want to look into this more in the future. And now some details about the mission concept. So now LGWA is very challenging, expensive. We have a recent estimate that it will cost a bit more than $1 billion. But that also really depends on some details and can still change in both directions, I would say. But the thing is that we want these 4 seismic stations operating in this very cold environment for, let's say, 10 years, okay? That's our goal. Now, nobody would, fund this as a first mission. You need a pathfinder. You need to understand more about the moon. There are important question marks, as I said, and we have to deploy a station, a geophysical explorer, in one of the permanently shadowed regions at the lunar poles, and make a not so long, maybe a few month long observation of the seismic background, of the temperature changes, of the magnetic field, and have all of this characterized, and then reevaluate our models of all of these effects, and then come up with a final plan for the LGWA mission, and then hopefully deploy that one later on. So this here is our current goal, and our main effort goes into realizing this Pathfinder mission with reduced sensitivity. So now we're talking about maybe picometer, sub-picometer sensitivity, even at 1 Hertz. So this is less challenging and technology-wise also easier to realize. Okay, now essentially, however, our stations are seismometers, very, very, very fancy seismometers, where, since they are truly gravitational wave detectors, you have to be careful about many more details than designers of seismometers typically are. So every little source of vibration has to be avoided inside these payloads. You have to be very stable with the temperature. You have to push material quality to the extremes. The readouts here, we are foreseeing at the moment a very compact laser interferometer to read out essentially the displacement of a proof mass with respect to the frame here. That's how seismometers work. So all of this is really pushing limits, and none of this is at the moment verified with the performance we need. So when it comes to LGWA, there are really still important steps to be done in the development of these technologies. Not so for soundcheck. Soundcheck, the Pathfinder mission there, the sensor is very close to to a higher technological readiness, let's say, to formulate this in a slightly vague way, because also for soundcheck we do have to still do some technology developments. One of the, some of the highlights that I want to mention, for example, a group in Hamburg led by Oliver Gerberding, they have done a really, probably it's a kind of a record for a laser interferometric readout of displacements. They have demonstrated essentially sub-femtometer or better than femtometer sensitivity at above 10 Hertz, getting to the LGWA requirement almost, with a scattering shoulder that is currently producing most of the excess noise that they are still observing. So they have to do something about it. And then they will still need some other improvements. But this is really much closer now than what I would have expected to be doable now or in the coming years. So this is one of the really big steps forward. Then we have a collaboration between a group in the University of Camerino, Max Planck Institute in Germany, and then the NPL in India on superconducting actuators. So essentially, the suspended masses, the proof mass has to be actuated on. And we are planning to do this with superconducting coil actuators, where this is essentially a thin film coil deployed on some substrate. And then in this case here, it is niobium nitride. And at some point, this already a year ago, essentially a bit more than a year, they were demonstrating this transition in superconductivity at 14 Kelvin, which was a bit lower than what was really expected initially as temperature. But in any case, this has been an important demonstration that we can build these coils with transition temperatures, well-marked transitions here. And so that is something that we have to keep working on. What we would like to get here is a coil like this out of a material that is superconducting at the temperatures of the PSR, so that we don't need any cooling in our payload. That is our wish, but we are not yet there. So 14 Kelvin is too low in temperature. Then we also need, together with the development of the sensors, we also need test facilities. And one of them is in Belgium, called E-Test, which is being constructed as part of the Einstein Telescope R&D activities. Similarly, really with Gemini, which is the experiment that I'm involved in, which will be underground, deep underground, 1.4 kilometers underground here in the Gran Sasso National Laboratories. And so there will be this pair of chambers, vacuum chambers. Inside there will be these relatively large suspended platforms, like 2-meter diameter platforms. And then on one of these platforms, we will essentially build a cryostat or a cryo box, a cold box, if you want, inside of which we will test our payloads. So we will emulate the temperatures and the low seismic background as best as we can, the conditions in the PSR in this facility, so that we can test all of our instrumentation inside that facility and hopefully be able to demonstrate these very challenging payloads to reach TRLs of 6 or so, which is really the step that you want to have before you give this to companies to build the final product. Okay. Of course, the fact that this is deep underground is helping us a lot because the seismic background all year long is extremely low at LNGS. So that is a winning factor for sure. There's a lot of synergy with other missions, concerning multi-messenger observations with X-ray, optical, and radio telescopes. Now, multi-band observations, I already mentioned this with LISA-type detectors, with terrestrial detectors. So there's also very strong synergy. Any studies of the lunar interior and seismicity is important to us. So there will be seismic experiments on the moon in the next years. For example, the Farsight seismic suit, for example, the Chinese Chang'e 7, maybe the Lunar Geophysical Network later on. So these would all greatly help us as well because they will all contribute to a better understanding of seismic backgrounds and the lunar interior, which is really very, very important to us. And we also have to understand the lunar surface environment, meteoroid impacts, magnetic fields, and so on. For example, there is a LUMIO mission being prepared at the moment. That will be a satellite that will go to the far side, that will orbit around the Lagrange point behind the far side of the moon and trying to observe impact flashes directly from the satellite instead of doing this from Earth, which will overcome certain limitations of the current flash observations. Okay. Very quickly now through some, where we are at the moment. So we have a team of these are groups that are, let's say that meet, to talk about payload developments. Now, not all of them have funding for LGWA. In fact, at the moment, only in Italy, we really have obtained funding from our space agency for LGWA. So the Italian Space Agency has started to fund this earlier this year. And we spent this money now to develop specific components of soundcheck and LGWA. And now these groups here, or these, the people behind it, they have essentially signed a letter of intent to form a payload consortium and to continue developing these technologies and payloads. Now, this is how, just to give you an idea what is involved here, there's a proof mass and the suspensions, the laser interferometer, the data acquisition and control electronics, superconducting core actuators, the sorption cooler in case we do have to cool, because that depends on the superconducting materials, the platform and the leveling system, the mass lock and release, the laser, and the test facilities. So there are really various components that we have to pay attention to and that are being developed. Now, a bit more about our activities. So we have submitted various times white papers to, for example, calls of NASA, the national academies in the US, ESA, and so on and so forth. So this also shows the fact that we were able to submit to so many calls also tells you that LGWA is really quite rich in applications and interest in the sense that we do have this connection to lunar science, we do have the connection to astrophysics, to cosmology, and that really allows us to be attractive to various directions and fields in science, which is really part of the reason why we have so many white papers submitted. Also, the mission is quite complex. And so we might profit from humans deploying our instruments. It's not necessary, but it might, if it becomes a possibility, could greatly reduce some of the risks that we have in deploying our instrumentation. now, scientific studies are augmenting in number. I mean, this is a very young experiment and for sure doesn't yet produce, science output like, other experiments, but we are there, we are looking into things and, there are people in China, in the US, in Europe, publishing papers on the lunar gravitational-wave antenna. So this is finally taking off. Also really stimulated, I would say, by the white paper, the Lunar Gravitational-wave Antenna, the Mission Studies in Science case paper, which is giving you a very good overview of what we believe to achieve with that detector. We are a collaboration of more than 200 members now from 18 countries. We are organizing our activities in working groups. They meet. Feel free to contact me if you want to join. If this is something that might interest you, then let me know. I can always subscribe you to these working groups, inform the coordinators of these groups that you would like to join. So it's about lunar science and site studies. Site selection, for example, falls here under this one. The instrument science, what are the developments that we still have to do to realize our payload. We have an outreach team and so on. So there are many well-organized activities at this point inside our collaboration. Now about the timeline, and I believe that this is already my last slide. Now, of course, we don't know the timeline. We cannot because we don't even know if we will get a launch, okay? So the status is at the moment that we are trying to get there, to convince one space agency to subscribe to this and say like, okay, we will move forward. We will find you a launch. We are not there yet. We do have contacts with all the major, well, not the all, but with important space agencies, ESA, ASI, ISRO, for example, and then maybe also less direct contacts, but they also exist in China. So we do try to push this forward, but there's no guarantee yet that it will happen. This said, given our understanding of the technologies and the challenges that we face, we believe that the sound check could be deployed in the early 2030s, and that LGWA could be deployed in end of 2030s or early 2040s, and then remain there for many years, 10 years or what. And at that point, it would observe for sure in parallel to future terrestrial detectors like Einstein Telescope and Cosmic Explorer. Very unlikely will we be able to realize overlap in time between the LISA mission and LGWA, because to make that happen, LISA needs a long mission lifetime, and that is not guaranteed. And LGWA has to happen really optimistically, near 2040 or so. If that comes together, then we might even be able to observe together with LISA. If we have all three bands covered at the same time, that would be amazing gravitational wave science and multi-messenger astronomy that we could do. Like that is something that is very, very clear and would be amazing. But okay, as I said, it's more a dream at the moment than something that we can hope to realize really. Okay, that's basically it, and that's where I want to stop. Thank you.
Thank you very much for the nice talk. Are there any questions? Okay, if people don't have one right now, maybe I can start with one. You spoke mainly about the astronomy. Is there also something we can learn about fundamental physics with the lunar gravitational wave antenna, like, for example, probing gravity, like that there are some scattering patterns which we can combine with other frequencies or other wavelengths?
Yeah, that is a very interesting point. That comes mostly because of the multi-band observations. So if you want to do what you need to test GR the best you can is to essentially estimate your waveform the best you can given your models. But now these models, they have 10, 15 parameters, and it is difficult, for example, to distinguish between not knowing the parameters of this model very well, or actually discovering that the model itself is wrong, but that actually there's modified gravity in play or something like that. So to make that distinction, you have to be really, to do it well. Of course, we are already doing it today. So already today in LIGO Virgo data, people are doing these tests. But let's say if you really want to push it to the extremes, what you can do in the best is to do this multi-band observations where you have perfect would be like a long time observation in the decihertz band or potentially even at lower frequencies with LISA. Then get certain information out of your signal about, in these frequency bands, and then learn something completely different very accurately at a different frequency band. Now, if you put this all together, all the observations from the different frequency bands, you can achieve a very, very accurate understanding in terms of your parameterized model of your waveform, and then really try to look for smaller and smaller deviations from general relativity. And so this step from to this multi-band observation that would enable a lot of interesting study when it comes to fundamental physics. That is not the only thing, though. I mean, you could, of course, count also a lot of cosmology under fundamental physics. For example, the formation of primordial black holes and so on. And that is definitely something where LGWA or any decibels detector would be quite strong in, because the mass range that it would observe at high redshift is quite interesting also from that perspective. So, but yes, we definitely can do a lot of fundamental physics as well.
Thank you. Yes, Louise?
Hi, thanks for the talk. Can you confirm that the lunar gravitational wave antenna will be able to detect signals from intermediate mass black hole binaries?
Yes, it would be actually ideally. So it's ideal for that, by the way. So there's the decihertz detectors can do this better than any other type of detector. So I had this somewhere before, but yeah, exactly. So let me go here. Essentially, if you look like how far out LGWA can see binary black holes. Um, 10 solar masses, for example, where the terrestrial detectors are very strong, LGWA would see only to, fractions of a redshift, like 0.1, 0.2 in redshift, not further. But the IMBH binaries, it would see out to redshift of several, few to several 10. So that is, and that allows you really to study that population to high redshift.
Yeah, I was thinking that regarding test of gravity, this could help in determining whether black hole uniqueness holds or not by comparing to other bands where you detect stellar mass black holes or maybe even supermassive black holes. This is potential.
Right. You're right. Good point.
Okay, very good. Thank you.
Other questions? Maybe I can ask another one. Basically, when you have the lunar gravitational wave antenna, how strong is the overlap between different signals? I mean, we have a lot of white dwarfs. I don't know much how many estimates, what estimates are there for white dwarf and neutron star binaries, but I guess there are also a few. So how strong is the overlap of between the signals, and how can we distinguish them?
Yeah, so what I can say is that we will definitely not end up with a problem similar to LISA, where the white dwarf background from the galactic white dwarf background is really posing you an insurmountable challenge. Now, also the detection numbers that we expect, at least, of course, this is an unexplored band, but if you take the models that we have into account, then the detection numbers that we expect with LGWA are much smaller than Einstein Telescope, for example. Now, Einstein Telescope, to tell this, is expected to see hundreds of thousands of signals per year, mergers of black holes and neutron stars. Now, it turns out there people did start to argue like, but what do you do? Because there you definitely have temporal overlap between detectable signals. A lot of temporal overlap. Essentially, at any moment in time, you will have a few thousand signals in the data that you can potentially detect. Now, it turns out that the temporal overlap doesn't really matter at the end of the day. It makes some things a bit complicated to start with, but at the end of the day, you can come up with methods of analyzing these signals that allow you to disentangle them despite the temporal overlap. Now, given, however, the fact that the number of signals in LGWA is expected to be much lower by a few orders of magnitude. Like, maybe we're talking about thousands of signals that we will be able to see with LGWA per year. Now, that essentially means that there's definitely no issue at all with disentangling those signals. Now, that depends, however, on the sensitivity that you reach. That's not a statement that is true for all decihertz detectors. If you take the really ambitious one, like the SIGO and Big Bang Observer, they again will see so many signals that they do have to come up with very clever ideas how to essentially remove all of them from the data, resolve them, and look for even weaker and weaker signals in the data. So that is a very big challenge for the very best concepts that we currently came up with for decihertz detectors, but not for LGWA.
Thank you. Are there other questions? If not, I suggest I stop the recording now.